So you've got a problem, right? Your first instinct is probably just find the answer, get it done. But what if I told you that the way you get to the solution is actually way more important than the solution itself? Today, we're going to look at why the how of solving a problem can be the difference between getting an instant answer and, well, an impossible one. The secret ingredient here is a word you've probably heard a bunch and something you use every single day, even if you don't know it. It's an algorithm. Now, forget all the complicated computer science definitions. At its core, an algorithm is just how you get to the solution. It's the recipe, the step-by-step plan. And seriously, we use them for everything. Following a recipe to bake a cake? Yep, that's an algorithm. The little series of loops and pulls you do to tie your shoes? That's an algorithm too. And when your GPS gives you turn-by-turn directions? You guessed it. It's just a set of instructions to get something done. All right, to really see why the how is such a big deal, let's put two different methods to the test with a pretty simple math problem, finding something called the greatest common divisor, or GCD. All that means is we're looking for the biggest number that can divide into two other numbers perfectly, with no remainder. So here's our challenge for today. What is the greatest common divisor of 60 and 24? We're going to solve this exact same problem in two totally different ways. Think of it like a race, a competition between two algorithms to see which one is smarter and, more importantly, which one is faster. First up, let's meet contestant number 1. We'll call this the slow and steady method. Its official name is the consecutive integer checking algorithm, which pretty much tells you its whole strategy. It's logical, it's thorough, but as you're about to see, it's not very clever. Okay, so here's how it works. It starts with the smaller of our two numbers, which is 24, and it asks, does 24 divide evenly into both 60 and 24? Well, no, it doesn't work for 60. So what does it do? It just goes down by 1 to 23. Does 23 work? Nope. How about 22? Still no. It just keeps on counting down 1 by 1 by 1, checking every single number on the way down. So after trying 24, 23, 22, and on and on and on, it finally gets to the number 12. Does 12 divide 60? Yep. Does it divide 24? Yes, it does. Perfect, we've got our answer. But to get there, this method took a grueling 12 steps. Sure, it got the job done, but man, it took the long road. All right, now for our second contestant. This method isn't new at all. In fact, it's ancient. It's called Euclid's algorithm, named after the Greek mathematician who figured it out over 2,000 years ago. And it is a much, much more elegant way of thinking. Euclid's approach is just genius in how simple it is. Instead of counting down, it uses division remainders. First, it divides 60 by 24. That gives you a remainder of 12. Now here's the really clever part. It takes that remainder, 12, and divides the previous number, 24, by it. What's the remainder this time? 0. The algorithm sees that 0 and stops. And the rule is simple. The last remainder you found that wasn't 0, that's your answer. And just like that, we have our answer. It's 12. The exact same answer as before, but this brilliant method found it in just 2 steps. Not 12. 2. That is a massive, massive difference. I mean, this comparison really says it all, doesn't it? On the left, you've got the brute force approach that just plods along, taking 12 steps to get there. On the right, you have an elegant and efficient algorithm that gets the very same result in just 2 steps. This is the power of choosing the right algorithm. So you might be thinking, a difference of 10 steps, who cares? For a small problem like this, it's not a huge deal, you're right. But in computing, problems are almost never small. They are massive. And this is where that little difference in efficiency starts to blow up into something absolutely gigantic. Think about it. What if you weren't looking for the GCD of 60 and 24, but two numbers with like hundreds of digits? That slow and steady method might literally take longer than a human lifetime to finish. Meanwhile, the elegant one could probably still be done in the blink of an eye. This is where efficiency becomes everything. So let's take searching, for instance. If you have to check every single item in a list of 128 things, that's called a sequential search. Worst case scenario, it takes you 128 checks. But a smarter algorithm, like a binary search, is way more clever. It works like looking for a name in a phone book. You jump to the middle, see if your target is before or after, and bam, you've just eliminated half the list. By repeating that split-in-half trick, it can find the same item in a maximum of just 8 comparisons. That's efficiency in action. And the stakes can get even higher. Just look at this. We're trying to calculate a number in the Fibonacci sequence. A fast, step-by-step method finds the 40th number almost instantly. A slower method, which recalculates things it's already figured out, takes over a minute. Okay, now let's try the 200th number. The fast way is still instant. The slow way, it would take an estimated billions of years. This shows that a bad algorithm isn't just slow, it becomes completely and utterly impossible. And this gets to the real heart of why this all matters. It's not about memorizing just one solution. It's about building a mental toolbox. The whole point is to have a whole repertoire of techniques so that when you're faced with a new challenge, you can choose the right tool, the most efficient algorithm for that particular job. So I'll leave you with this thought. Every time you're using an app or a website or any piece of technology that just feels sluggish and frustratingly slow, ask yourself, is the computer slow, or is it just running a really bad algorithm? It makes you wonder how many of these elegant, super-fast solutions are out there waiting, and how many slow, brute force methods are still hiding in the code we use every single day.